All right, welcome back. Today we're going to be talking about curve sketching. How do we take a function and sketch its curve using all the different techniques that we have learned thus far? And this includes some concepts that you should be familiar with from algebra, as well as some brand new ones that you have come across in calculus. And so in order to sketch a function, you're going to want to pay attention to these 7 steps of gathering information about a function that you can then use to draw a rough sketch of it. And so when you're getting ready to sketch a curve, you want to make note of the domain. You want to know where is your function defined, right? What x values is my function defined for? And that's naturally going to lead in discussing continuity, right? Where is your function not defined? Where do you have breaks in the function? Where are there asymptotes? Where are there holes? Those kinds of things, right? So domain and continuity kind of go together. And then as a result of determining the continuity and the domain, you might also come across some vertical and horizontal asymptotes. And then you're going to want to determine where your x and y intercepts are. And these are essentially just the points where your function crosses the x-axis and the y-axis. And that is something that you learned how to do in algebra. And then the last 3 steps all deal with calculus-related concepts, that first one being differentiability, so that would mean you take the derivative of your function and see where the derivative is defined, and then of course you would set your derivative equal to 0 to find those critical points and determine your relative extrema, and then finally you would want to use the second derivative to determine your inflection points and the concavity of your function. And so before we go through an actual example of sketching a curve, I'm going to do a short review of what the first derivative and the second derivative tell us about a function. But before that, I just want to remind you that the lessons on your screen here right now are going to be very helpful in prepping you for curve sketching. So if you actually haven't seen my videos or my lessons on these other topics that you see on the screen, I would recommend that you go ahead and check those out. I have the playlist for all my calculus videos in the description of this video. But now let's do a quick review on what the first derivative and the second derivative tell us about functions. So let's start by looking at these 3 different examples of a type of function that you might come across. If we have a function like this, where as you move from left to right, it is pointing in the upward direction, then your function would be increasing. And that would also mean that the first derivative of your function is positive. That would mean your slope is positive for that function. If you have a straight line, then your function is going to be constant, and that means that the slope is 0, or that your first derivative would be equal to 0. And if you have a function where as you go from left to right, it is moving in the downward direction, then your function would be decreasing, and your first derivative, or your slope, would be negative. And so that was just a very brief overview of what the first derivative can tell us about a function. And so now let's review what the second derivative tells us about a function. If we have a part of a function like this one right here that is concave up, then that means that the second derivative, f double prime of x, is going to be positive. And if you have a function that is concave down, such as this one, this is concave down, then your second derivative, or f double prime of x, is negative. And so what the second derivative is telling us in each of these cases is what is happening to the slope. In our first case, where the second derivative is positive, that is telling us that the slope is increasing on this function. And in the case where the second derivative is negative, that's telling us that the slope of the function is decreasing. And so now that we've reviewed all the different things that the first and second derivatives tell us, let me show you a little chart that I think is going to be helpful in drawing different curves for a given function. So if you take a look at this chart here, we have the first derivative in our top row, and then we have the second derivative in our middle row, and then we have some different curves that are going to correspond to the signs in the columns. And so what we find is that if our first derivative is a negative value, but our second derivative is a positive value, then that means that our function is decreasing at an increasing rate, right? The function is decreasing, but the slope is increasing as we move along. If we have that the first derivative is positive and the second derivative is positive, then that means our function is increasing at an increasing rate, right? Our function is moving upward from left to right and the slope is getting greater. And then we see if the first derivative is positive and the second derivative is negative, then our function is increasing at a decreasing rate, meaning the function is increasing from left to right, but the slope is slowly decreasing as we get higher. And then finally, we see if the first derivative is negative and the second derivative is also negative, then our function is decreasing at a decreasing rate. We are decreasing from left to right, and the slope is getting smaller. And so this is going to be very helpful because when we go through the curve sketching process, we're going to be drawing out the number line like we did when we were determining intervals of increasing and decreasing, as well as intervals of concavity. So we're going to kind of put those two things together, and that's going to help us see how our function would curve. And so it's going to be very beneficial for you to know the shapes in this chart. And so with that being said, let's finally get into our example of sketching the graph of a function. All right, so for our example, we have sketched the graph of the function f of x equals 3 times the quantity x squared minus 4 divided by x squared minus 9. And so the first thing we want to do when we sketch the graph of a function is determine what its domain is. And so in order to do that, we have to think about what values of x our function is defined for. And so for a rational function like this one right here, we'll set our denominator equal to 0, and that's going to tell us where our function is not continuous or where it's not defined. And so if we do that, we'll have x squared minus 9 is equal to 0. And if we add 9 to both sides, we'll have x squared is equal to 9. And then if we take the square root of both sides, we'll have that x is equal to plus or minus 3. And so what that tells us is that our function here is not defined at the values of -3 and +3. And so our domain in this case would be the following. We would have the values from -infinity to -3 unioned with the values from -3 to 3 unioned with the values from +3 to infinity. And so this is going to be the domain of this function. And so in terms of the continuity, which is the next thing that we would be interested in knowing for this function, we found that our function is not going to be continuous at those two values, x equals plus or minus 3. And so then the other thing that we learned from that is where we have vertical asymptotes, because vertical asymptotes are found from setting your denominator of a rational function equal to 0. And so then we know that we have those vertical asymptotes, which I'll write as VA for vertical asymptote, at x equals -3 and x equals +3. And so now that's going to be the first thing that we will draw on our graph. And so if we bring the graph up here, we can now add our vertical asymptotes at -3 and 3. And if we draw those asymptotes, we need to locate x equals 3 and x equals -3. And so that's where we'll draw these dotted lines to represent our vertical asymptotes. All right, so now that we have drawn in our vertical asymptotes, we also need to figure out where our horizontal asymptotes are, if we even have any. And so if we look at our function here, the way we're going to determine where we have horizontal asymptotes is to remember something that we learned at the very beginning of calculus when we talked about limits, specifically when we looked at limits at infinity, or when x approaches infinity. And so what we did was when we took the limit as x approaches infinity of different functions, we found that that would tell us where we had horizontal asymptotes. And so while we could go through and take the limit of this function, I would rather use the little trick that we learned from using the limit at infinity to help us determine where the horizontal asymptotes are. And so that trick is to look at the terms in your numerator and denominator and look at the coefficient of your term with the highest degree. In this case, our two terms with the highest degree in the numerator and denominator would be this x squared and this x squared. Now, both of them have the same degree of 2, and so what that means is that the horizontal asymptote is going to be located at the value that is found from dividing the coefficient of the numerator term by the coefficient of the denominator term. In this case, if we multiply this 3 through the top, the coefficient of this term would be 3, and the coefficient of this x squared would be 1. And so our horizontal asymptote would be at y equals 3 divided by 1, which is y equals 3. And so just for reference, the other two rules that we know is that if the highest degree in the numerator is less than the highest degree in the denominator, then your limit was equal to 0, which means that your horizontal asymptote would be at y equals 0. And if the highest degree in the numerator was higher than the degree in the denominator, then you would have no horizontal asymptotes. All right, so now we found that we have a horizontal asymptote at y equals 3, and so now let's draw that on our graph. All right, so then let's draw in our horizontal asymptote, which we know is at y equals 3, and so we'll draw an asymptote right across there. All right, so now that we're done with that, we are ready to find our x and y intercepts of our function. And so to find the x-intercepts of our function, we're going to set our function equal to 0 and solve for x. And so if we do that in this case, we'll have 0 equals 3 times x squared minus 4 divided by x squared minus 9. Now, if we solve for x in this case, we're going to have to multiply both sides by the denominator, and that's just going to completely eliminate this denominator because we're multiplying it by 0, and so we're going to have that 0 equals 3 times x squared minus 4. And so then we can set this quantity equal to 0. So we'll have that x squared minus 4 is equal to 0. And so if we added 4 to both sides, we'd have x squared equals 4. And then if we took the square root of both sides, we would have that x is equal to plus or minus 2. And so now what we find here is that our function has two x-intercepts at x equals positive 2 and x equals negative 2. And so our 2 points are going to be negative 2, 0 and positive 2, 0. And so now we can go ahead and plot these on our graph. All right, so we have our two x-intercepts at x equals 2 and x equals negative 2. And so I'll plot those points right there. All right, so now that we have plotted our x-intercepts, now we want to find our y-intercept for our function. And we find our y-intercept by plugging 0 into our function. And so in that case, we would have that y is equal to 3 times 0 squared minus 4 divided by 0 squared minus 9. And so now if we simplify that, we'll have y is equal to 3 times negative 4 divided by negative 9. And so y is going to be equal to negative 12 divided by negative 9. And so then those negatives would cancel, and 12 divided by 9 is going to give us that y is equal to 4/3. And so then that means that our y-intercept is going to be at 0, 4/3. And that's about 1.33 repeating in decimal form. And so let's go ahead and plot this y-intercept on our graph as well. All right, so our y-intercept is going to be on the y-axis at the mark of 4/3 or 1.333. And so that's going to be about a third of the way up to 2. And so I'll put it right about here. That is going to be our y-intercept. All right, so now we have successfully taken care of all of the algebra concepts related to sketching the graph of our function. Now we're ready to move on into the derivative of our function. And so I'm going to clean up the work here, and then we're going to move on into our first derivative. All right, so now we're going to take the first derivative of our function. And if we do that, you can see that our function here is a quotient of two functions, so we're going to need to use the quotient rule. And so f prime of x is going to be equal to the following. And I'm going to have the quotient rule up here on the screen for you to reference in case you need it. And so now as we go through this derivative, it's going to be a little annoying to have this 3 out front of our top function. And so since that's just a constant multiple, we're going to kind of pull that out. So what I mean by that is we're going to rewrite our function to just be 3 times the quotient of these two functions. And that's going to make it a little bit easier for us to take our derivative. So I'm going to write that over here as well. Because remember that when you take the derivative of a function times a constant multiple, you can just pull that constant out and then multiply it by the derivative. So that's going to make this a little bit easier to handle. But our top function in this case, when we use the quotient rule, is going to be x squared minus 4, and then our bottom function will be x squared minus 9. And so if we go through with the quotient rule, we'll start by taking our bottom function, x squared minus 9, and multiply it by the derivative of the top function. And the derivative of x squared is going to be 2x if we use the power rule, and the derivative of negative 4 is 0. So you're just going to have 2x. And then we'll subtract the original top function, so we'll have x squared minus 4, and then we'll multiply this by the derivative of the bottom function. And that's going to be 2x as well, so we'll also have 2x. And so then in the denominator of our derivative, we're going to have the bottom function of our original function squared. So we'll have x squared minus 9 squared. All right, so now we're going to want to simplify our first derivative here. And now I apologize, I'm going to skip a few steps here. I'm going to skip right from this form of our first derivative to a more simplified form. And all there is to do is to distribute this 2x into the parts of this quantity and this 2x into this quantity, and then you add together your like terms. Just don't forget to distribute this negative to each part of this quantity. But I'm going to skip all that work to save some time, but I would encourage that you go through it yourself to make sure that you get the same first derivative that I'm going to get. Because if you simplify this, you'll have that the first derivative, f prime of x, will be equal to 3 times negative 10x divided by x squared minus 9 squared. This would be your simplified version of this derivative. And so now what we want to do is we want to determine the differentiability of our function. And so to do that, we just check the continuity of our derivative. And so if we check the continuity of our derivative, we set the denominator equal to 0. We'll have that x squared minus 9 equals 0. And then if we solve for x, we'll have x squared equals 9, and that x is equal to plus or minus 3. And so in this case, we find that our function is not differentiable at x equals plus or minus 3. All right, and so now what we want to do is we want to take our first derivative and set it equal to 0 to find our critical values that have the potential to be either a relative min or a relative max. And so if we were to set our first derivative equal to 0, notice that the denominator here is not going to matter because it's going to be multiplied by 0. And so all we're going to have is 0 is equal to 3 times negative 10x. And if you multiply 3 by negative 10, it's not going to matter. You'll have negative 30x. Either way, you'll find that x is equal to 0. And so this is going to be the only critical value that we get from setting our derivative equal to 0. But we actually have two more critical points, and that is our 2 points of non-differentiability. Remember that a function also can change from being increasing to decreasing around points where your function is not differentiable. And so when we perform the first derivative test and we draw our number line, we're going to want to remember to include those 2 points where our function is not differentiable. So we're going to have that one critical point that we found from setting the derivative equal to 0 of x equals 0, and then we'll also have negative 3 and positive 3. And so before we move into performing the first derivative test, I'm going to clean up my work a little bit so that we have enough space to do it. And so now we're ready to move on with our first derivative test. And we can see that our 3 intervals here that we're going to be using will have negative infinity to negative 3, we'll have negative 3 to 0, 0 to positive 3, and then positive 3 to positive infinity. And so now we're going to want to pick values of x between the endpoints of each of our intervals and plug them into our first derivative to see if the value is positive or negative, and that's going to tell us where our function is increasing or decreasing. And so I'll start with our first interval. I'm going to plug in negative 4 into our first derivative. And so I want to apologize in advance here. I'm not going to be showing the work of plugging in these values into the first derivative. And so what I recommend that you can do is pause the video and plug in negative 4 into the first derivative yourself and see if you get the same value that I get. But if you come across any issues, feel free to let me know in the comments and I'll try to help you out. But if we plug negative 4 into our first derivative, we will get the value of 120 divided by 49. And that is a positive value of our slope, which means that our function is increasing on that interval. And so I'll put a plus sign for that interval on our number line. And then if we test the value for our second interval, I'm going to pick negative 1. So we'll have f prime of negative 1, and that will be equal to plugging negative 1 into our first derivative, which if you do that, you'll get 15 divided by 32. And that is also a positive value for our slope, which means our function is increasing on that interval, and so we can write another plus on that part of our number line. And then for our third interval, I'm going to pick positive 1, so we'll have f prime of 1, and that's going to be equal to plugging 1 into our first derivative, which will get you negative 15/32, and that is a negative value for our slope, so our function is decreasing on that interval. So I'll draw a negative sign on that part of the number line. And then for our final interval, I'm going to pick positive 4, so I'll have f prime of 4, and that's going to be equal to negative 120 divided by 49, and that is also a negative value for our first derivative, and so that means that our function is decreasing on that interval, and so we'll label that on our number line as well. And so let's look at our potential relative extrema here of x equals 0, and what we see is that our function is changing from increasing to decreasing around that point. And so that means that x equals 0 is going to be a relative extremum, specifically a relative max, because the first interval around that point is increasing. And so what we have is that at x equals 0, we have a relative max. And now if you want to get the full point so that we can plot it on our graph, you're going to want to plug 0 into your original function. And if you'll do that, you're going to get the point 0 4/3. And so that's actually not a new point that we can plot on our graph because we already plotted it, because this is actually our y-intercept. But just keep it in mind that that y-intercept at 0 4/3 is a relative maximum. It's going to be the highest point in that area of the function. All right, and so with that, we are done with the first derivative. But now let's move on to our second derivative to see if we have any inflection points and where our function is concave up and concave down. All right, so I cleaned up our work a little bit, and so now we're going to take the derivative of our first derivative to find the second derivative of our original function. And so if we do that, f double prime of x, or the second derivative, is going to require that we use the quotient rule on our first derivative. But if we go through with the quotient rule, we'll have that our top function is negative 10x, and our bottom function is this quantity right here. Now, don't forget about this 3. In fact, I almost forgot about it, so let's just add that in here real quick. We're going to have 3 times the rest of that derivative. And so we'll start by taking our bottom function, which is x squared minus 9 squared, times the derivative of the top. And the top is negative 10x, and so the derivative is just going to be negative 10. And then we're going to be subtracting the original top function, so that's going to be negative 10x, multiplied by the derivative of the bottom function. And so that is going to require the chain rule, because this is a composite function, right? Our inside function is x squared minus 9, and our outside function is this quantity squared. And so if we take the derivative of the outside function first, we'll have 2 times x squared minus 9, and then you would subtract 1 from your exponent, so you just have 1, but we don't typically write the first power, and then we need to multiply by the derivative of the inside function. And so in this case, the derivative of x squared is going to be 2x, and the derivative of negative 9 is 0, so we'll just be multiplying by 2x. And that is the end of the top part of our derivative. And now for the bottom, or the denominator, we are going to take the bottom function and square it. So we'll have x squared minus 9 to the 4th power. And so then that is the end of our derivative process. We have now used the quotient rule and we have our second derivative. And so I'm going to apologize in advance again. Just like we did for the first derivative, I'm going to skip some of the work of simplifying our second derivative to a nicer form. I'm just going to give you that nice form right away. But before I do, I will give you some pointers here so that you can kind of see how to go about this simplification. Just notice that you have this x squared minus 9 quantity in this term on the top and this term on the top, as well as in the denominator. So you can actually cancel that out of your function, and so then this one will become 1, and this one will become 3, and so then that would make it a lot easier for you to simplify. You'll just have negative 10 distributed into this quantity, and then you would multiply negative 10x times 2x, and then you just have to add your like terms from there. And so to save some time, I'm not going to go through all that work, but hopefully you can do it, and you will be able to check your result with what I'm going to give you right now. And that is that the second derivative, or f double prime of x, is equal to 3 times 30 times x squared plus 3 divided by x squared minus 9 to the 3rd power. That is going to be your second derivative. And so let me clean up the work a little bit here, and then we will try to find our potential inflection points. All right, so I cleaned up our work here. I kept what was important. We have our second derivative, and we have our important results from when we used the first derivative. And so now let's find our potential inflection points by setting our second derivative equal to 0. And just like with the first derivative and our original function, the denominator is not going to matter in this case because you're just going to be multiplying it by 0, and so it's just going to be completely eliminated. And so when we set our second derivative equal to 0, we'll have 0 is equal to 3 times 30 times x squared plus 3. And if we simplify that a little bit, we'll have 0 is equal to 90 times x squared plus 3. And so then we can set this x squared plus 3 equal to 0. So we'll have x squared plus 3 equals 0. And then we'll have x squared equals negative 3 if we subtract 3 from both sides. And now we can see that if we were to take the square root of both sides, you can't take the square root of negative 3 and get a real result. And so in this case, this equation has no solutions, which means we have no potential inflection points for our function. The concavity is not going to change at a point on the function. However, it still might change at the points where our function is not continuous. And so if you look at our graph so far, we have those vertical asymptotes at negative 3 and positive 3, which is where our function is not defined, where it's not continuous. And so those are the points that we're going to use to help us determine where our function is concave up and concave down. And so let's erase this work because we found no potential inflection points, and let's just go through with determining the concavity of our function. And so if we draw a number line for the second derivative here, and we'll label that, and again, we're going to be using the values where our function is not defined, where it's not continuous, and that's going to be at negative 3 and positive 3. And so now we see that we have 3 intervals that we're going to test for concavity, and so I'll write down those 3 intervals here. And now we're going to test values on the second derivative between the endpoints of each of our intervals. And so I'll start with our first interval, and I'll plug negative 4 into our second derivative. And so once again, I'm going to apologize in advance. Just like we did for the first derivative test, I'm not going to show the evaluation of plugging negative 4 into our second derivative. However, I would encourage that you pause the video and see if you get the same value when you plug negative 4 into the second derivative that I'm going to give you right now. And so I highly encourage that you pause the video as we go through these values to make sure that you see where they're coming from. And so if you plug negative 4 into the second derivative, you'll find that it is equal to 1710 divided by 343. And so that is a positive value for your second derivative, which means that your function is concave up on that interval. And so we're going to have a plus sign for that interval. And so then for the second interval, I'm going to plug in 0. So we'll have f double prime of 0. And if you plug 0 into your second derivative, you will get negative 10/27. And that is a negative value for your second derivative, which means that your function is concave down. And so I'll write a negative sign on that part of our number line. And then we'll pick a value for our last interval, and I'm going to choose +4, and we'll plug that into our second derivative. And if you do that, you'll get 1710 divided by 343, and that is a positive value for your second derivative, which means that your function is concave up on that interval. And so I'll draw a plus sign on that interval for our number line as well. And so now with that, we are finally done with determining where our function is concave up and concave down. We are done with the second derivative, and we're done with the first derivative. Now we are ready to sketch the graph of our original function. And so in order to help us do that, I'm going to erase this work here, and we're actually going to combine the results from our two number lines onto one number line and then reference that chart that I showed you at the beginning of the lesson. And so in order to combine our number lines, I'm going to draw one new number line here, and then we're going to put together what we know from both derivatives on one number line here. And so let's label all of the points from each of our number lines. We have -3, 0, and 3 on our one for the first derivative, and we have -3 and 3 on our one for the second derivative. And so we just have -3, 0, and 3 to label here. So we'll have -3, 0, and 3. And so I'm going to put all the signs for the first derivative on the top here, and we're going to put all the signs for the second derivative on the bottom. And so if we add our first derivative signs to our number line, we will have plus, plus, minus, minus, right? That was what we had up here, and I just moved it to this number line. And so then for our second derivative, it's going to be a little bit different because it doesn't exactly translate over because we didn't have this 0 over here. But you can see that from -infinity to -3, we were positive. So I can put that in on this number line. And then we also see that from 3 to +infinity, we were positive. And so I'll put that there. And then between -3 and 3, we were negative. And so between -3 and 0, we're negative. And between 0 and 3, we're negative. And so I'm just going to draw a negative sign for both parts there. And so now what we can do is we can remove these two previous number lines and then just use this combined number line to compare to our chart from the beginning to see how to draw the curves for our function when we sketch the graph. All right, so I made our problem a little smaller and then moved our number line up to the top. And so now if we make our graph bigger, we can now see how we're going to sketch the graph of the function. All right, so to sketch our graph, what we need to do is we need to look at our number line and see what is happening with our first derivative and our second derivative. And so we can see for our first interval from the negative values of x up to -3 that our first derivative is positive and our second derivative is positive. And so what that means is that our function is increasing and our slope is increasing. And so the shape of our function is going to look like this. And then you can draw in your arrows. Now I know it's above the horizontal asymptote because if you were to plug in a value over here, let's say -4 into your original function, you would find that the output would be a little bit over 5. And so that's going to be above y = 3. And so if you're ever not sure where your function is going to be located, just pick a point somewhere along that interval and see what your output is. And that'll tell you what side of the asymptote you are on. But that's going to be the shape of this part of the function given our number line. And so then hopefully the next part of our graph, this middle part, will be the easiest because we know that this point right here, this y-intercept, is our relative maximum. We found that at the point 0, 4/3 that we had a relative maximum. And so we know that this is going to be the highest point in this general area, which just from looking at our x-intercepts leads me to believe that our function is going to look like this. And I would continue in that direction. And so let's see if this lines up with our number line. We see that from -3 to 0, our first derivative is positive, which means our function is increasing, and the second derivative is negative, which means the slope is decreasing. And so you can see that for this part of our function is increasing, but the slope is decreasing. Our slope is higher here than it is over here. It is slowly decreasing. And so then we see that for our interval from 0 to 3, that our first derivative is negative, so that means it is decreasing, which we see on our function here, and the second derivative is negative, which means that the slope is also decreasing, which is also true here. It is getting more negative as we move along the function. And so then finally, if we look at our last interval from 3 to +infinity, we see that our slope is negative, which means our function is decreasing, and that the second derivative is positive, which means that the slope is increasing. And so the shape of our function is going to look like this. And we can draw our arrows there as well. And so this is going to be the sketch of our graph. And you can check all the shapes of these curves with that chart that I showed you at the beginning and compare it to our number line. It's going to match up. So if you're having trouble drawing your curves, you're not sure which way they should go, try to keep that chart in mind and compare it to your number line that you create as you go through the process of gathering all that different information to draw your graph. All right, and so that's all I had for this lesson. If you want to see another example, I'll have an example video linked at the end of this video as well as in the description. If you have any questions, leave them in the comments below. But if you don't have any questions, this is all I had for now, so I will see you next time.